So welcome, everybody. My name is Scott Shaw. I'm one of the hosts of the Thoughtworks Technology Podcast here. And the topic today is going to be TinyML. And we'll find out what that is in a second. But there are the three other people here that would like to introduce themselves. So Rebecca, do you want to go first?
Sure. This is Rebecca Parsons. I'm another one of the recurring hosts for the Thoughtworks Technology Podcast, and I'm here to be the peanut gallery. Andy, do you want to go next?
Yes, I'll go next. So I'm Andy Nolan, Director of Emerging Technologies at Thoughtworks Australia. Really excited to talk about TinyML today. And Matt, would you like to go next?
Yes, hello, my name's Matt. I'm a software engineer, machine learning person at a TinyML startup called Edge Impulse. So long-term ML person, and more recently focused on the smallest of small ML. So.
And Matt used to work with us at ThoughtWorks, and we were sorry to lose him, but we were also excited about his new venture. And before that, he was at Google, doing some of the work there that's gotten some renown. Let's start out with some definitions. Andy, you're the first person that brought this to my awareness, I guess. And I wonder if you could give us a bit of an overview of what are we talking about with TinyML?
Yeah, for sure. So TinyML, the name says a lot. So it's a very small version of what we typically know as machine learning, and it focuses on deploying models to sometimes the smallest devices possible. So think microcontrollers, Raspberry Pis, those types of devices. And it does have its constraints around what you can do with it, but it also has a whole bunch of opportunities it opens up. Because it does run on small devices means it can often be battery-powered devices. Latency is a lot lower because the data source and the model are really close together. And it also gives us the ability to scale these things into places where we probably don't typically consider locations for machine learning. So because of their disconnected nature, we could deploy them into harsh environments at the top of a mountain or at the bottom of the ocean. They don't need that connection with the cloud compute to actually do the inference around the model.
Is that the only place when we don't have access to cloud computing? Is there, even in the presence of cloud, is there still a place for this small devices?
Yeah, absolutely. I think if we think about our cars or even our phones as devices that merge the worlds between cloud compute and edge compute. So often when you're using your phone, there'll be many models running to do face recognition on photos or even voice detection and things like that. And as an end user, you don't actually know where that model's running. And sometimes you don't even really care where that model's running, as long as you're getting that user experience. So we're seeing more and more developers embedding machine learning into the edge compute component of their software systems and enhancing the user experience like you would on your phone or something like that. We're also seeing it deployed into cars. So we can think about a car as a software-defined vehicle that has a whole collection of sensors running. Ideally, the compute would be happening as close as possible to where the data's occurring, just because you don't want latency in a car, right? However, there's other attributes within a car, sometimes around the user experience, that could occur in the cloud. So the navigation and these types of things could be occurring in both of those locations. And as an end user, you don't really mind where that's happening as long as you're getting the best of both worlds.
Yeah, a lot of privacy related stuff as well there. There's no reason why you can't use something very tiny to basically protect the user's core data and just basically ship up the minimum sort of requirement to do something useful. But even if you're the aggressive person on the other side capturing the data, you can't sort of reverse engineer any other information about the person. So that's a big one. And many times they do exist next to each other in what we call cascades, where you've got some sort of first model whose only responsibility really is to very cheaply and quickly decide whether it needs to double quotes wake up a later model somewhere. It might be on a bigger device or it might be all the way to the cloud. And you see that with text transcription or wake words on a phone. They often have three pieces. There's a tiny super low power chip in a phone whose only job it is to decide whether the last bit of audio sounds like something that might be worth waking the CPU up. And then the CPU might go, oh, actually, that's a bit hard. Or I might send that one off to the cloud because I sort of need to cascade it along. So often it's not just about one or the other. It's about how these things sort of decide to poke the next one down the chain.
Yeah, that was going to be one of my questions as well. How cooperative are these various models, both in the cascade that you're talking about, and as well as, potentially across peers? Is that something that we're starting to see more, where maybe you've got, a lot of sensors and they are sharing data with their, and nearest neighbors or something, so that everybody's kind of got a sense of the neighborhood? Is that something that is that occurs in this as well?
Yeah, absolutely. In industry, there's cases, and they're pretty rare. A lot of the times, especially because it's early nascent field work, we can get a lot of really low hanging fruit with just this dumb sensor that's sitting on one device and sort of doing something useful. And in those cases, it's like the absolute nightmare in terms of cloud scenario, because you expect this device to be burnt into something that's read only. It's going to be attached to this big vibrating greasy machine for the next 5 years, and you're never going to see it again. So it's like the exact opposite of what you might get with the cloud. But yeah, totally, there's this idea about mesh related network stuff. And the analogies with networks is very, very common. You can think about these machine learning models as only being really responsible for packaging up some sort of really high frequency data that might be coming along in a useful form to then add to the mesh. So it really starts to blur the lines about what these things are sort of really responsible for, because when you've got something that is now working with bigger models down the chain, or it's working with peers that are sometimes sort of, nearby, whatever that means, it's no longer this really simple sort of input in, prediction out. It can be very flexible with what these things are sort of aiming to do. And the constraints are often around things that Andy alluded to that are really unusual, and they're not really something that a web dev or someone who's like a classic ML ops engineer is really thinking about. It's like, how much does it cost in terms of power usage to access this bit of memory? It's like, I would have never thought about that with a big fat GPU that's like burning my house down effectively. But this starts to become really important. And again, it's that cadence of sort of the deployment cycle. All the things that we know about ML ops that have really taken off in the last 5 years are almost completely irrelevant when it comes to the idea that you're going to be deploying this thing, and it's sort of a one shot. So it's really interesting to see how do you carry the lessons learnt about building models when they're so differently in terms of how you actually operate them. So
are there different kinds of models? Are they the same models that you would use in a large system, or do you have to constrain them in some way?
Yeah, so constrained is the underlying word there, and I feel like one of the, it's a funny thing about neural networks, for particularly, that their biggest win in terms of the class of models they represent, is they have this sort of free parameter idea where you can scale a model independently to what the input or what the output is. And this has been the growth of the success of neural networks over the last 20 years has been around, let's make really big data sets, and we can scale the networks accordingly, even though we're not sort of changing what we put in and out. Now, that works the other way too, in terms of edge stuff. So it's actually it touches on one of the reasons why I left very, very large computing, because neural networks. It's because we were building models that were just so big, it was like becoming vulgar displays of power on how many GPUs you could throw at it. And I feel like, a lot of the art and the sort of, beautifulness of building these things was lost. I know that sounds a bit ridiculous, artistic, but anyway. So, but yeah, so the other flip side now is like, how small can you make them? And these models are tiny, and it's that constraint idea. How do you now take away from the sort of types of models we've built these days? How do you strip them back to their core based on these constraints to make them useful? And, there's lots and lots of things to do around these, the ways we approach this, and a lot of still hanging low hanging fruit. So, it's very early days for this field.
I love that we can talk about the aesthetics of our technical solution on here. That's I think about that as well. But I tend to think of, and you kind of alluded to this, of machine learning as requiring massive amounts of data, not something like that one individual could even collect and train to for a specific application. Is that the case? Like, where do you get all the data to train these real world devices?
Yeah, there's a really old rule of thumb that is, like all rule of thumbs, a little bit wrong in that if you have a neural network that has 10 parameters, then you need 10 training instances. This is something that's been in my head since day one. But it's never one-to-one, but it talks about the fact that as you make models bigger, you have to make data sets bigger. So if you go the other way and you've got a really small model, you can sort of argue then, oh, I don't need much data. But it really then starts to talk about what is the complexity of the question you're now asking of the model. So if you have some huge complicated vision model that, is doing really fine discrimination between breeds of dogs or whatever, then it's fair to not really expect that to do terribly well on a TinyML model where the model is a millionth of the size of a big one. But that doesn't mean that you can't frame your problem as something that is like very, very, very simple, in which case it doesn't need much data. Say, for example, a day or night detector or something that's really, really simple that could work on a very low resolution image. We can sort of build something that is useful. So it's a lot around the times about the scaling of the class of problems. Now, the other thing that's really interesting is when you talk about data for feeding a supervised model, we often think about, like, say I'm doing image classification. My data is a bunch of images and a bunch of labels for that. The TinyML has an interesting sort of scenario that we, as sort of siblings of these tiny models, are these absolutely enormous models that have already been pre-trained. So when we talk about supervision and gradient descent for building these models, it doesn't have to be the raw inputs and outputs. It can be what other models think about these sort of things. So there's a whole class of these ways of training we call distillation, where the input to the TinyML training isn't data sets, it's what does this other big model think about things. And that's really interesting because, if you're building one of these models out and you're sort of trying to build some sort of pipeline about how you train these models, you often have the use of other models as the primary source of sort of input data. So if you've trained, the point I'm getting to is if you've trained a huge model or someone else has trained a big model for you, like ImageNet, which has hundreds of millions of examples, and you have access to a model, which we certainly do now, you don't need as much data anymore because you're sort of using this big model as a bootstrap to sort of direct the small model in the right direction. So you can get quite a way. So any concrete example of this is a ridiculous experiment I did recently. There's a generative vision model called Stable Diffusion where you can give it a text prompt and you can basically just sample and generate images. I ran up Stable Diffusion on my huge, big, fat desktop here and said, generate me, I can't remember, 100,000 images of a screw on a workbench. Now generate me 100,000 images of a bolt on a workbench. I use those images downscaled to train a TinyML model, and it sort of works okay because the constraint now of what we're trying to sort of decide is quite small. So in terms of what did I use as a user, I just gave 2 textual descriptions of what I wanted the thing to do. And then behind the scenes, there's this big CPU burn, which is basically materializing information from this large model to just really narrow down to then train that small model. So it's a really interesting question. How much data do you need? Because we have access to things now that we maybe didn't have before.
So you shrink the solution space down for the small models from what the large model is, and you can do it with a lot less resources then, I guess.
Absolutely.
One of the things that I've noticed about when people are talking about these applications is that it's usually working on streaming data. It's a continuous process. I wonder if that presents any particular challenges that would be different from one of the big cloud solutions that we see.
Yeah, it's that latency thing that I think Andy alluded to. A lot of industrial industry sort of problems are around streaming data. It's classic sensor data. You've got some machine that's vibrating and you want to know, does that vibrating mean that you're about to fail in the next day? In which case I should tighten your bolts now before you fail. So yeah, some streaming data, audio related stuff, wake words, those sort of things, very much are around that very, very short round trip, which definitely doesn't work well with cloud related stuff. It's one of the main motivations they had to put things on a phone was because the round trip latency was too slow to go to a cloud to do wake word detection. No one wants to wait 50 milliseconds for something. So yeah, it's a big one. Streaming data as well, often the ways that it's funny, it's a bit embarrassing. It's like the classic, the best ML is no ML. But a lot of the streaming related things we do with, say, very high frequency data, vibration, that sort of stuff, it's solved primarily using very, very old classic digital signal processing stuff. And the actual neural networks, double quotes, we put on the device to do something sort of, just very flat linear regression type stuff even. So, and again, the beauty of neural networks, if you take a neural network and you keep turning things off, you get to something like logistic regression, which is like this super old technique that is fundamental. So the practical side of things is that in the TinyML space, again, based on the modality of the data and the sort of, low-hanging fruit, the ML part is sometimes a little bit, embarrassingly small.
Well, and thinking about a lot of the examples that we've been talking about so far are this real, okay, you flash it and then you forget it, with the sensors and such. Are there applications, other than, okay, I've trained my iPhone to recognize my face, so I don't have to type in a PIN except every 2 weeks. But can you think of more sort of out in the wild applications where maybe you are using some kind of tiny reinforcement learning, or there's interactions that would modify that model over time?
Yeah, anomaly detection is a really big one. The idea that you don't really know what's anomalous on a particular device until you sort of get to it. And so, that's a huge, huge market in terms of predictive maintenance. It's a mammoth one. So the staging usually is that sort of 3 sort of steps. One step is like, how do you sort of set the model up to do its best in terms of before it sort of leaves the nest? And then the second stage is what can you do on device to sort of do training on the fly, and which might be some anomaly detection type stuff. And then, how do you, if at all, get stuff back to base in terms of, sort of training data? Because one thing that really surprised me, and it's obvious in hindsight, but I hadn't really thought about it at the time, is that if you're doing something on a microcontroller, you don't have much working space. You really have enough memory to do something interesting in the next 10 milliseconds, and then you sort of throw it away to get the next bit of streaming data in. So if you want to do like sort of long-term collection of data, it's often with an attached device that's, very particularly there just for the point of providing storage. So though we can do things on the device, it's often around this sort of fine-tuning type stuff. It is definitely difficult. That's not to say that there's not lots of cases where there are things in a mesh and they're sort of talking to each other. It's just the extreme we always have to think about is this idea of the single shot of the model. And more, as infrastructure gets better and, tooling across a network of industrial plant, you can do on-the-fly updating of models. So, models are getting, the actual device is getting big enough to handle the idea of an over-the-wire update and stuff. So, it progresses and progresses and gets better and better in terms of these updates. But we're still in a lot of regime of like one-off.
At the start, Matt, you mentioned that TinyML challenges a lot of the ML ops approaches that we use today. So machine learning engineers will train a model, deploy it, and slowly refine that and monitor its accuracy over time until they finally get something that works. And it gives them the ability to adjust that model to its environment so it's as realistic and as close as possible. In contrast, TinyML doesn't give you that ability sometimes. How does that change the development process? Does it push a lot of that, the iteration right back to the lab? So you need to maybe simulate more or change the way you do things because you've really got that, in a lot of cases, just one shot to burn it to a sensor and then it's off in the wild for however long. How have you seen that sort of challenge that ML ops idea?
Yeah, it's really about that sort of embarrassing waterfall type approach of saying, I've got to collect a bunch of data up front, which is, and there's a whole industry around the idea of how do you collect that data. These what we call bricks, which are these devices that sort of, you might say to someone, I'm going to have put this brick on your industrial devices for the next month or whatever to collect fundamental data. And then we'll take that data away and then we'll sort of do the model development and then we'll deploy. So it can be iterated, but it's just the things that we assume are really cheap in online web type stuff like parallel models or just logging every bit of inference that goes through a model. They're just really difficult to do. So it's much more traditional. Collect a bunch of data, train a model, deploy that model. Even the monitoring is really difficult. How do you, once you've got this thing that's running on a microcontroller and, the only reason you could really deploy it in the field was it was only going to cost $4 per device to send across this, manufacturing plant of 1,000 devices. how are you going to monitor them? How do you even know they're working properly? What's the operational version of this? It's really difficult and certainly unsolved.
And what is the workflow, the kind of typical workflow for somebody who's building one of these models and getting it on a device?
Yeah, it's funny that there's two real key personas that sort of I've seen in this area. There's one where there's like an ML person who's a bit more like me, who comes from the ML side of the things and is interested in the embedded. And then the other one's the embedded engineer, who's the person who knows how to actually write some bizarre C++ code to get this working on, bizarre bespoke tool chain they're using, because it's complete Wild West. When you think about the silicon side of things, everyone's got their own compilers and you have to use this SDK on this chip, and you're using this other chip, it's this other thing. It's all over the place. So those embedded engineers who are very specialized in that type of area don't know much about machine learning. So the flow is really interesting at the moment. There's a lot of, not conflict, but there's a lot of butting of heads when you try to go from the idea about how do I train a model to how to actually deploy the model. It's funny as well, the one thing I've really noticed, and it's the elegance often in tech industry of us, we build layers on things, which build layers on things, which build layers on things. And so it's easy to take a model nowadays. Like I could, even if I don't know much about ML, I can Google search for a while and find like here's a model that does something. MobileNet, that's cool. Like I'll just download, here's a Colab, I'll grab that Jupyter notebook. Oh, cool, I'm trained a model. But it's so easy to do and to build something valuable, but have absolutely no idea how it works under the hood. So it's funny to see a lot of people we work with that are embedded that they're running these ridiculously large models that are like 100 times bigger than they need to be, just because it was the simplest thing for them to do. So I feel like that's happening a lot, that we've got people who are embedded that don't really know the machine learning, but are able to get something working because they're in that low-hanging fruit. They get something simple, but they're going to experience pain pretty soon when they try to do something more complicated. But the tooling is there's a real mismatch cadence between the tooling. There's I might train in TensorFlow, for example. TensorFlow has a part of its sort of library ecosystem called TensorFlow Lite, which was sort of developed for phones. And then there's another part of it, which is like TensorFlow Lite for micro, which was developed for the microcontroller type stuff. But it's all still quite, weird. I have to run this command over here. It's like, if you look at a bit of code to do this, you can really see the sort of levels of abstraction and where they break. There's this real elegance and beauty around these abstract methods to call, get a data set, train a Keras model, it looks really nice. And then there's this horrific, bizarre bit of code where I make some converter to convert to TF-Lite. I'm like, I don't know what's going on. So you can really see, whenever I see a bit of code that's like that, it really sort of illustrates the fact that these bits that have these really bizarre bits of code that aren't at the same levels of abstractions around it mean that these haven't been unified yet as frameworks. They're sort of very cobbled together. So it's certainly not solved. There's a lot of hard work you need to do to make things work.
So I'm a programming languages geek, and so I have to ask, since you mentioned C++, and I know in other contexts like autonomous vehicle technology, there is a move to adopt Rust as opposed to C++. Is there any of that going on in the TinyML world, or is it still very firmly in the C++ world?
I think it's very firmly in the C++ because there's no agreement between silicon sort of manufacturers to have a real standard for how you write a bit of code, except for C++. So it really is still the canonical thing. And yes, it goes back to that Wild West comment of like, if you want to actually deploy something on a microcontroller, you get to this point where you need to you've got a bit of C code or whatever it might be, C++ for running inference, and then you have to run, or even if you have maybe a TensorFlow graph. So you've trained a TensorFlow model, you want to run this on a microcontroller. The TensorFlow graph becomes a symbolic representation of the compute, which then goes through these compilers to get it converted to different bits and pieces. And so you end up having to find, for this particular silicon provider, their weird bespoke tool chain that I have to download. And it only runs in Windows. I have to run in a VM or something. And now I've got some weird exe I have to run that takes a TF-Lite graph and spits out some .bin file that I flash. So the fact that it's all this Wild West and this certainly not standardized means that we're sort of forced as sort of the common denominator to stick with something like C++. But yeah, to be honest, and again, it's an interesting thing. I haven't learned as much embedded as I would have liked. I was talking to someone about this the other day. I'm still an ML person, not an embedded engineer, but one day maybe.
So sorry for the detour, but like I say, I'm a languages geek.
No, I'm fascinated with it. There's a language that we've been using more and more that's called JAX that I've sort of jumped on the bandwagon quite a while ago. And there's this whole compiler technology called XLA that Google has provided. And, it's nothing to do directly with TinyML, except it is. So, Google had this, here's a random diversion. Google had this huge farms of GPUs from NVIDIA. They realized they can't be stuck with it forever. When you get to a large enough scale, it's worth building your own ASICs for doing compute. So there's the development of the TPU. If you're developing your own sort of ASIC like this, you need to put hard software abstractions between what you're doing and the sort of way you're deploying, which turned into this series of compiler technologies called XLA, which is this accelerated linear algebra tool chain. It's more formally under these open things like MLIR now, but it gives us this level of abstraction in the software that we write things in this sort of symbolic graph that get spit out, so to speak, to GPU kernels or to CPU code. And the reason I bring it up is because more and more there will be targets from this compiler language, which is a particular, CPU sort of microcontroller. So one thing that we've been playing with a lot is this this idea that a language like JAX gives us this intermediate representation, which means I can pull in NumPy and I can sort of go through JAX, and underneath TensorFlow now, if you start to dig a little bit, you get to XLA because it's what they're using under the hood. So it all becomes this muddy one thing under the hood. No longer is TensorFlow just TensorFlow. It's something that sits on top of XLA, which means that I can approach it from different angles. The reason I bring this up is because the language becomes more and more free, and these sort of intermediate compiler languages mean that I'll be able to write Rust, pass it to this XLA. The XLA compiler will just spit out some binary microcontroller code optimized in insane ways. So it's changing. If we were to do this podcast in 3 months, it'd probably be quite different again. It's really under churn at the moment. It's really interesting stuff.
Are trends in the hardware space? Like, I don't know what the popular deployment platforms or microcontrollers or embedded devices, but is that changing? Are there any big trends there now?
I feel like the whole supply chain stuff that's been happening the last couple of years has had some interesting directions about things. I feel like the more and more as useful applications are sort of demonstrated through the use of a microcontroller, the more microcontroller silicon providers want to get on the bandwagon and sort of sell people stuff. So I feel like the most interesting general thing, I think, is around sensor fusion, because at the moment you have an idea that you might have a sensor, especially a very high dimensional sensor like a camera, that is very different to vibration sensor in terms of its acquisition, the complexity of the information it gathers and how much memory it takes and stuff. And at the moment, architectures are still hardware-wise very separated. You have a camera that acquires something, and then you pass it off to sort of a machine learning model running on a chip. And if we're talking about more and more this idea of sort of not disposable but one-off built things, then they start to merge a little bit in what they are. Why not start to put things around the sensing actually more directly in the memory that the devices are using? So and in some ways it's the most interesting trend, I think, the idea that the sensor and the compute for it become almost the same thing in a sense. And there's these ridiculous examples of my most interesting one, I think, it's from about a year ago, where someone, and I'm going to get this totally wrong because it's been a while, but someone developed this idea of a memory layout on a chip, like an actual piece of memory that you write and read from this bit of memory at the lowest level. And they worked out a way to express the read from the memory to have as a side effect the calculation of dot products. Now, dot products are like this fundamental part of linear algebra that is used in all of machine learning. Everything we do in machine learning these days is just lots and lots of matrix multipliers, which are lots and lots of dot products. So they'd worked out through this really bizarre scheme a way of doing these types of calculations as a side effect of the memory read, which is just ridiculous because suddenly it's insanely fast. Now, if you attach, we're going to have the idea that maybe CCDs and the idea of the way we acquire information from a visual sensor gets more and more connected to the memory as well. So, in 5 years, we might have this idea that your sensor is actually doing the compute as well. So why not sort of burn into the actual CCD the way we lay it out, a feature extractor that says that this little camera module I'm giving you isn't a camera module in the sense that it's spitting out RGB. It's spitting out some learnt, interesting representation, low order dimensional representation, that is then useful for a neural network downstream without you having to have this 10 million parameter convolutional neural network. So that's just a really rambling answer to your question, Scott. But
it was a rambling question, so that's okay.
Yeah, but I think yes, to this idea of fusion, I think that's the most interesting thing. How do you find two bits of hardware that are close to each other, that are serving a common goal, and actually make them the same bit of hardware?
Hey, Andy, part of your job is to be a bit of a futurist and kind of look at what are the potential industrial uses, or where are these things being done now, and what are the potential business implications for that? I guess the first thing, is this a future thing? Is this something, or is this a practical reality now?
Yeah, I think, and Matt mentioned this earlier, I think the most common application for TinyML today is around wake word detection. So for our smartphones, all of our voice assistants, they're using TinyML to listen to the audio stream and detect very, very few words, simple words. And we all know what they are. I won't say them because all of your phones will probably go off. But that is an example of TinyML. It's embedded. There's dedicated hardware in our phones these days to do specific tasks like that. And we're already seeing it. So when we talk to people about TinyML, they're like, I've never heard of that before. And when you explain how it's already part of their everyday lives, they all of a sudden realize it's something that's here today. It's not a futuristic thing. That's one example. And Matt has been mentioning a few other examples that are starting to come out in industrial IoT applications for preventative maintenance and anomaly detection and these types of things. I think we'll begin to see more and more of this in the future, where it's embedded in smartwatches and activity monitors, and you can buy pillows that detect your sleep patterns and all of these sorts of things. That's where we'll start to see more and more of these machine learning models being deployed at the edge. And it has its challenges, but it also has its advantages around privacy, latency, and all of these sorts of things. So imagine you can start to use models now to detect things that you probably wouldn't be comfortable sending to a third party or a cloud provider. Maybe it's health data or something about you that's inherently personal that you wouldn't want to share. All of a sudden, we can start to use these very narrow, specific devices to service those applications that maybe otherwise we wouldn't have a way of dealing with. So I think we'll begin to see it more and more. And I think machine learning engineers will start to develop the skills that are appropriate for these types of applications. What I'm hopeful is that machine learning engineers don't always default to just deploying things into the cloud, and start to look for opportunities to deploy things closer to the edge. If it's on a microcontroller, fantastic. But if it's on a phone, that's also really good as well, because there's these unique user experiences that we can create with these models that otherwise wouldn't be possible because of latency and privacy and things like that.
Yeah, as tooling gets better, you just get more and more people thinking they've got a problem and the tooling's easy. They'll just sort of solve it. We have a really common use case, which makes me laugh, but if it works, it works, where if you're retrofitting a large old industrial system that uses water pipes, for example, or gas pipes, and you've got analog dials that you're sort of literally sitting some old gauge, why not stick a vision model on it that literally reads the dial and then pings off as a digital thing what the dial is reading? It sounds ridiculous, but if it's trivial to do, then why the hell not retrofit things if it costs $100 or something? So these sort of things, I love them in the sense that they're, if you sort of put your formal academic hat on, you're like, that's ridiculous, overkill. Like, why would you bother using a convolutional net to do this? Well, it's like, well, it's actually, if it's really easy to do and really cheap and it adds value immediately, then why would you not do it? So I feel like the better tooling gets and the easier things become, then the more ridiculous ways people will work out to stick this sort of stuff everywhere.
One of the things that we sort of alluded to before was what you can accomplish with lots of these devices working together. I think it's kind of fascinating to think about lots of these tiny smart devices working together to create some kind of emergent behavior that is smarter than the sum of them put together. And I know, Andy, you've talked about composable AI. Is that a similar concept?
Yeah, for sure. So the idea is that we have these small devices that do one very specific task well. And if we can combine different types of devices together, we end up with these systems that are composed of small AI devices that create this more intelligent or more interesting thing. So again, cars are a great example of that, how we can have a sensor that detects whether it's dark outside or not to turn on the lights. We combine that with proximity sensors and all of these other sensors. All of a sudden, we can start to create these eventually self-driving cars or even driver assist features that together are really, really interesting. Another great example is VR and VR headsets. So if you think about a VR headset, it's all about the user experience. So the latency in processing the visual information, the gesture information, the movement of the head, the sound, audio, all of these sort of things need to come together for this device to be successful. I can see a future where TinyML is playing a really key role in at least pre-processing some of that information so that it can enrich it for further processing maybe later on. And together with all of those TinyML systems embedded in that headset, we get this greater user experience that hopefully is more immersive and realistic than it otherwise would have been. So yeah, I really like that idea of taking these very simple, kind of dumb devices, adding them together to create these really intelligent systems like cars and VR headsets and things like that.
Yeah, in my sort of layman's understanding, that's kind of how the brain works. Lots of modules, smart modules, but working together, competing and cooperating in different ways to create some larger kind of behavior.
Yeah, it definitely fits very well with how neural networks work. Like they're fundamentally they have this beautiful decomposition where you can sort of break them into what we've call this idea of layers or blocks, depending on how you want to structure things, where the only job of the network is to take some information and sort of transform it and then transform it again and then transform it again to some output. Usually it's a lot around the time, the idea of compression. Like if you have a vision model, you have this very high dimensional data coming in, but if you're classifying, is this a cat or a dog? You can think of the neural network as just incrementally compressing that very, very high dimensional image down to something that is just literally 0, 1. So the beautiful thing about it is that if you train a model that does this, you can sort of literally sort of chop them in half and you get the first part of the model whose job it was is to sort of learn interesting features from the high dimensional data that is only really used for the second half of the model. That ability to chop them up means that you can do some of the stuff that you talk about in terms of composability, where the job of the edge model, the thing that's in the factory where there's 1,000 of them, its only job is to learn some distilled version of what it's seen from this high dimensional, sort of very high frequency data in the last 5 minutes to ping off with a little Bluetooth ping off to some sort of central box, like a big Raspberry Pi sitting in the corner or something, that then collates that then turns it into sort of a useful decision in terms of monitoring the sort of the overall structure of the factory. So this idea that a lot of the common ways of the most successful sort of formulation of machine learning in the last 10 years for supervised stuff is neural networks, which have this great ability to be decomposed. So you can literally think of it as run the first bit of the neural network on the edge and then run the second part of the neural network back to base, so to speak. A lot of flexibility about how you sort of decompose and run bits in different places.
Our audience would probably like to know how they can get started with this? There's a lot of practitioners out there that might be interested in experimenting with themselves. And I wonder, what would your advice be to a developer who wants to get started?
Yeah, I mean, it's hard not to plug my own company, but there's a platform, Edge Impulse, that does this sort of thing. We have a lot of competitors, Neutron AI, for example, so Neutron. There's a number of platforms available, a number of frameworks that sort of are sort of made for either the embedded person or the ML person that are sort of coming at it in different ways. And that sort of all frame the problem as this 3 sort of step of curate the data a bit, build some machine learning model, deploy it to a device. And so you can go a long way with those sort of most use cases can be started with that general idea of, I have a data set, I train a model, I want to deploy it. And then as you go further and further and get more mature, you might decide, oh, I don't want the platform to do the first part, I just want the second and the third part. Or, I've got the third part handled, but not the first and the second. So more and more it is being approached, at least from a first sort of phase for a lot of people, as using one of these platforms. And then as they get more mature, sort of picking and choosing parts of the platform that they might want to integrate into a bigger part of their system. But yeah, it's still very early days, and it's very illustrative. I can tell you firsthand experience to try to build it from scratch in terms of first principles, like take a SDK from Arduino library or something, take TensorFlow and the way it exports TF-like graphs, and the sort of TensorFlow experimental conversion to some of these things, and to stitch it all together. It's very interesting in early days, and I think a lot of the platform sort of plays have come out of that pain.
Matt, given your background at Google and your long history with this field, I can't pass up the chance to ask you what you think of the topic nobody's discussing about generative AI, large language models. Are chatbots going to take over the world and ruin literature, or what's happening here?
Is the singularity here? Yeah. This is always the question I get. When's the AI taking over? No, it's funny. So maybe I would have been more interested in this 10 years ago when I was like really deep in NLP, large models. So to be honest, given some tiny problems I've been working on, ChatGPT, which is far from tiny, has been not in my radar to deeply look at. But I do, like all people, have opinions that I'm happy to talk about. I feel like the biggest thing with NLP, and it goes all the way back to classic natural language processing, there's 2 sort of fundamental pillars in NLP. There's syntax and semantics. And when you think about a model like a ChatGPT or all the models I ever worked with in NLP, they're very much trained on textual data, which is very much on the syntax side of things. So they're very, very good at being syntactically correct. Very good grammar, being able to write in the style of a person, all the sort of things you think out of syntax, the actual surface forms and the way it's written. So as prose gets longer and it's more coherent in terms of syntax, it can be quite convincing. So I think these models are very good at convincing people they're right. But the other pillar, which is really important with text, and a lot of the ways we use it, is semantics. What does it mean? Is it correct? Is it factually correct? So I feel like the more and more we have these models which make it trivial to generate text, because text is the ubiquitous modality of knowledge we have on the internet. So the ability to have a model that generates a bit of text that I can then cut and paste into a YouTube comment or a Facebook thing or make a bot to do it's very interesting what the large scale ramifications for that will be. But it's just text. There's nothing about it being correct in any way. It's convincing, but it doesn't mean it's factually correct. Now, for a lot of cases, who cares if it's factually correct? I want to write a Harry Potter alternate history or something, sure, spit out a bunch of very coherent, syntactically correct stuff. But if you start to now talk about it in terms of weaponization for political stuff and the fact that people would be reading this sort of stuff thinking it's factual, it worries me. That sort of stuff worries me. So that's I don't know. That's just an opinion, I guess, but it's certainly very interesting. Certainly very interesting.
It's an opinion. It's maybe more informed than a lot of the others that I'm listening to these days. So thank you.
Yeah. Yeah, it's fascinating. We used to work on knowledge graph completion. So the idea of building semantically correct knowledge that then is used in textual generation. And it's really hard. There's so many things when you start to talk about truth. What does truth mean? Like, did Harry Potter go to Hogwarts? Well, yes, he did, but no, he didn't, because that's fiction. It's not actually real, is it? So you can't say he did, or can you say he did? And if you think about something like, what's the capital of France? Oh, it's Paris. What about 1,000 years ago? It wasn't Paris anymore. What's the fashion capital of France? Is that Paris? Hang on, we're talking about opinion now. Is it objective? Is it subjective? Like, or as soon as you start to even think about any of these concepts, they get way muddier than you think they're going to be. So it's a fascinating problem space to deal with.
Okay. Well, thank you. This has been really interesting. It's always good to talk with the three of you. I've had many separate conversations with you, so this has been really good to get everyone together. Thank you.
Thanks.
Yeah. Thank you.
Thank you.